Okay, welcome. So this talk we're going to go through and derive the fluid equations, so particularly the Euler equations, using conservation of mass, momentum and energy. So these quantities are conserved, and we can use that to derive equations that we can solve and calculate properties of fluids. So here we'll focus on gases initially, but the same concepts and the same ideas will carry on and go into MHD, so plasma physics, so first single fluid and then two fluid later on in the lecture series. So for now I'll introduce some of the key concepts in fluids, try and keep things reasonably simple. As you'll see, it gets fairly complicated fairly quickly. One of the key concepts to start with is that we have to divide a fluid up into small pieces, so fluid elements or fluid packets. And the idea is that we have a whole system we want to solve, but we start by breaking it up into small pieces. And so we consider just a cube, for example, of fluid, like this one. And we have a small cube, and we're going to make it smaller towards the end. And we're going to start with this quite big cube, and then we're going to shrink it to a point very shortly. But we look at what's inside the cube and what flows out through the boundaries of the cube. So we have some kind of volume here, which we call V. It's just how much is stored inside. And we have surfaces around here. So if I call this surface here, let's label this here. We have a surface called S, and it has a normal vector which is just sticking out here. So we have a vector which points out from the surface. It's normal to that. So I'm going to give that a vector because it's pointing outwards from the volume. And we can look at what's inside the volume. So we can start with mass and then go on to momentum and energy. So if I just list that here, so we have conservation, and we have mass, we have momentum, and we have energy. So here we'll start with mass. So mass. So here we're looking at what's inside the volume. So if you just basically add up all the fluid that's inside, so we have the total mass, which is, say, kilograms. It's the sum or the integral over this volume. So I'll label that as the integral over V of the mass density, which is some function of x, of time and space, and that's integrated over the volume V. So this is time t and space x. Okay, and rho here is the mass density. So rho is some function of t and x. X could be three-dimensional here, and this is the mass density. So this would be in units of kilograms per cubic meter in SI, for example. Okay, so this just says I have a certain density of fluid, and I integrate that over volume, and I get a mass m. Okay, so that's inside the fluid. So far, so good. Then we can examine what happens when fluid is flowing. So what happens if it has some flow velocity? It will move out through these surfaces. So it could flow out to this surface or one of the other surfaces. And if fluid is flowing into the volume, the mass will increase, and if it's flowing out of the volume, it will decrease. And the way we write that is by considering the flux. So we can say the flow through the surface. So the flow, through the surface S. This is the integral, and now it's just a 2D integral, so it's an integral over a surface, rather than this was an integral over the volume over 3 dimensions. It's an integral over surface S of the mass density times the flow velocity. Now that's how much mass is flowing, so it's the kilograms which are flowing times the speed that they're flowing at, times integrated over this surface S. Now these are two vectors, so velocity is a vector quantity, and so is the surface. And what we want here is a dot product, because this is the flow which is going perpendicular to the surface. So S here points perpendicular outwards, and so if U is in the same direction as S, then it is flowing either outwards or inwards. So positive here means flowing outwards, and negative means flowing inwards. Okay, so that's the total amount of mass which is flowing across the surface. If we look at just the units of this, this is kilograms per cubic meter. Here we have meters per second, and here we have meters squared. And so the total units of this are, we have kilograms per second, and then per meter squared. It's the units of this bit. And then if we integrate this in area, ds, we just get kilograms per second. So this is how much mass, how many kilograms per second are leaving or entering the volume. And if it's positive, then they're leaving, and if it's negative, then they're going into the volume. And so we can write down an equation that the rate of change of mass with time. So we write down, so here we have dm by dt is the rate of change of mass with time, and the mass we derived up here. So this is this part here. Change color. So that was this equation over here. And so here we can use this to write down, this is the integral over the volume of rho dv, and this is changing in time, so it's d by dt. d by dt of this integral of rho dv, and this is changing in time because of these flows in or out of the surface. So this is minus, you have an integral over the surface, because we said if this is positive, then mass is going out, and if mass is going out, then the mass is dropping. So the mass is falling inside the volume if it's going out. So it's the integral over the surface of rho times the flow velocity perpendicular to the surface. Now if we integrate over the entire surface, so it's a closed surface, we can just write this. So this means integrating over the whole surface of the volume. Okay, so then this part, we can use Gauss's theorem, so you may have come across in electromagnetism, for example, to rewrite this surface integral as a volume integral. So you can write this as the integral over the same volume of the divergence of this flux rho u. And this is this bit bigger. That's a divergence. Okay, so now I have an equation which on both sides of the equation I have an integral in the volume, so rate of change of time of rho, and rate of change of and the integral of this divergence. And it turns out we can do a little trick, so we can make the volume, so the volume basically goes to 0. We make the volume smaller and smaller, and we say this equation works for any volume v, and so it must work at every point in space. So we can choose different volumes, we can make volume go to 0. And this equation inside the integral, so we have the d by dt of the mass from here, so d by dt of rho, and must be equal to the divergence of this, so with the minus sign here, must be equal to the minus divergence of rho u. So that has to be true everywhere, because this is true for any volume v. And so we can just write down the derivative form of this equation, and that's our first Euler equation, where we have the mass rho and the speed, the velocity of the fluid v. Now, unfortunately, this tells us how mass changes in time, but it doesn't tell us what this u is. So now, in order to work out how the mass is changing, we need to know what the speed is, what the velocity of the fluid is. And to do that, we need another equation. So for that, we need the momentum equation. Now, in general, we might have sources and sinks, so we might have a gas puff or a valve or a pump, which is putting mass in or taking it out. And we represent this by just adding another term here, just an S for source or sink. So it's just here, just write source or sink, depending on whether it's positive or negative. Now, this same equation, where you've got a time evolving quantity, motion of that quantity by fluxes and sources and sinks, is a very generic one. So this is common for many conserved quantities, and so you can actually use the same arguments for the other things like momentum and energy. And so momentum behaves a lot like the mass did. So we make the same argument that we have a conserved quantity, which is the momentum. So we have the momentum. We have just mass times velocity, and we have three components. So there's the momentum in the x direction, the y direction, and the z direction. We can write this in terms of a momentum density, just as we did with the mass. So we can write this as the integral over the volume of the mass density times the flow velocity. And this gives us a momentum density. And to keep things slightly easier for notation, we'll first look at each component separately here. So I write that, so u is a vector, so it consists of ux, uy and uz. So ux, uy, we have uz. So we have three components separately, and in Cartesian geometries this will be much easier. Later we'll look at non-Cartesian geometries, and there it's a little bit more complicated. But for Cartesian geometries, we can consider each component entirely separately. So for example, we can look at the x direction. So we can look at mu x, which is this integral of rho times u in the x direction here. And we can make exactly the same arguments as we did for mass density, because the momentum moves with the fluid. If the fluid moves, the momentum moves too, and so there's a flow of momentum across the surfaces. And so you can write down a flux for momentum. So we have an integral, basically, of the momentum density dv, and this is evolving in time. So we have a d by dt here, and it's evolving in time because we have momentum moving through surfaces, so in or out of the volume. And just like the momentum density, we can write down a very similar thing, that we have a minus, because positive means going out, the integral over the surface of the momentum flux. And the momentum flux is just the momentum density multiplied by the flow velocity. So it's how fast momentum is being moved from one point to another. So we have a rho ux, which is the momentum density in the x direction, and it's being affected by a velocity u, which is perpendicular to the surface. So very similar to the momentum, very similar to the mass density. Here you have momentum density that's being affected through surfaces. This gets a bit confusing because we have velocity here twice. So here it's simpler with just one dimension, and then we'll look into multiple dimensions very soon. And again, we might have sources and sinks here, so we might have extra terms on the right side. But like with the mass density, these equations hold for any volume, and we can turn this part here into a divergence. So we can write again that this is minus the integral over the volume of the divergence of this momentum flux. So rho ux affected by the velocity u, integrated over the volume. And so just like with momentum, these equations hold for any volume v, and so we have that essentially the d by dt of rho ux is equal to, and now we have this again, minus divergence of a flux ux u. And so there are extra terms we need to consider here. So with momentum, the sources are essentially forces on the fluid. So if we push the fluid, it will accelerate. And so here we have extra forces, which is called F. So these are external forces on the fluid, so it could be gravity, for example, but more immediately it could also be pressure. So if we impose pressure on the fluid, so we push on the fluid, it will accelerate and transfer momentum into the fluid. So again, we can consider what happens at the box of fluid. So we can look at a volume where we have a box here. Attempts to join over a box. Okay, so we have our volume of fluid, which is this volume V. We have the x direction along here, for example. This is the x direction. And we have momentum inside the volume, and it's being moved through the surfaces. And we have forces on the volume. So we have, say, this surface here at the front, and we have, again, a surface at the back. So if I draw that in here, there's a surface back here, and there's a force on the fluid on this side. So here there's a force, which is the pressure outside the volume. So there's a pressure, which is some function of x. Now the notation gets a bit confusing, so there's I have to be careful with how I write this. So there's P, which is the pressure, and there's rho, which is the density. So just have to make sure that the rows are curly and the P's will be straight and larger than the rows. So I'll try to be consistent with that. So there's pressure pushing on this side, and then if we consider this box has some finite width, so this width of the box here is say dx, and pushing on this side of the box is the pressure at x plus dx. So this other location here, there's also a pressure which is pushing back, and then the net force on this fluid is just the difference between the forces on each side. So we have a force on the side, and the force is just pressure times area. So if we just make a label for what this area is, we don't know what the area is, but we can just give it a label and it will cancel out in the end. So we give this as area, this is the area of this surface here, and we assume it's a cube so that this is that the area on this side is the same. You can handle different cases where the area varies, but this gets a bit more complicated because then you have the sides as well to consider. If it's just a volume, a square, or a cube, then this makes it much simpler. So here we have the area, we have the pressure, and we get the force. So the net force, so the force here is just the pressure on one side minus the pressure on the other side. So here we have a P at x times the area minus P at x plus delta x plus dx times the area. So that's the net force on this volume of fluid. Okay, and from that we can work out what those terms here should be. So what we can do is we can add it first to this term up here. So we say, okay, here we must have here must be a force. So force is added to this term here. When we go from a volume to a local quantity here, so derivatives, the force is the integral over the volume of this. And so we can write that this F is basically the force divided by the volume. And now the force we worked out, and the volume we can write down. So the force is this, the force on one side minus force on the other side. The volume of this box, if I write this down, so volume is just the area of this side, A, times this thickness, dx. It gives us the volume of the box. So it's just A times dx. So we can write down this expression for F appearing in here, which is essentially a force density, so it's the force per volume that's appearing here. So just like this is the momentum density, this here now is the force density, so it's force per volume. And this is just, so here we have P of x minus P x plus dx. And that's these two terms here, divided by the area. And that's the force, so the force on one side minus force on the other, all divided by the volume, which is A dx. I said that the areas would cancel out, and here they do, so here we have areas cancel. And we just have what looks here like this is the difference in pressure over a small distance dx divided by dx. And this, as the volume of the fluid gets smaller and smaller, this is just the derivative, which is the negative of the derivative. So this is just minus dp by dx. So this is just the gradient of p in the x direction. There's a minus sign because this would be p of x plus dx minus px would be the derivative. And so now we have an expression for this F, force density, is just minus dp by dx. And we can just put that straight back into here. And so we have an equation for the momentum in the x direction. So we have d by dt of the momentum in the x direction, and that's equal to minus the flux, like with the mass density, so it's rho ux, as vectored with a velocity u, and it's changed by forces on the fluid. So we have minus dp by dx. Now, if p has multiple dimensions, then this becomes a partial derivative. And in fact, when we use multiple dimensions, we can write down the same equation for each component. So you'd have a d by dt of rho uy with a uy here, and a dp by dy in here. And the same for the z direction. So uz, and a d by dz. And so it's more convenient to write the whole thing as a vector. And so we just write the momentum equation as d by dt of rho u, where u is now a vector, divergence of rho u minus, and then here we have a gradient in each direction, so it's just the grad p. So this looks a bit confusing initially, because now we have two u's in here, but just understand that this is three equations basically written out, one for each component of u, and that's the momentum equation. So that's the second Euler equation that we've derived there. Okay, so now we have an equation for the momentum. So we have equation for the velocity of the fluid, which is what we needed to be able to calculate the flow of mass. So an equation for rho involved calculating u, and now we have an equation we can use to calculate u. Unfortunately, it now involves this extra quantity p. So to calculate the flow, or the change of the flow velocity, we need to know the pressure. And to do this, we need to introduce the third equation here, which is the energy equation. And this will allow us to calculate this pressure. So energy, if I write down here, so here we have the energy equation, energy. Okay, so energy here is, I'm going to call this E, so this is the energy density, it's the energy per volume of fluid. And this has two components, so it has the internal energy, which is the part due to the random motion of the molecules, so the pressure of the gas, plus the kinetic energy, which is due to the bulk motion of the fluid. So here we have plus, and then the kinetic energy is just a half mv squared. And so if you have a energy density, so it's divided by the volume, so you have a half, then rho u squared. So u here is the flow velocity, this is mass density, and so this gives us an energy per volume as the units, so it's joules per cubic meter, for example. This internal energy depends on the state of the fluid, of the gas. So it depends on what kind of gas you have. Most time, we're going to consider ideal gases, because this is what's most appropriate for plasmas in most cases, and it's what's used in deriving Euler equations as we're doing here. So E is this internal energy. Internal energy is E, and this, let's say, for an ideal gas, is just 1 over gamma minus 1 times the pressure. And so for a monatomic gas, this is just 3 over 2 times pressure. So this gamma is the ratio of specific heats. So that's ratio of specific heats. And it will depend on whether you have molecules or atoms. For atoms or individual particles, as we have in plasma, so protons, ions, electrons, this just becomes 3 over 2 times pressure. And so the energy has two components. We have a part due to the internal energy and part due to the bulk motion. And when we write down an equation for how this behaves, because the integral of this energy density is the energy. So if we integrate E over a volume, E dV, this is the total energy inside that volume. And so if we consider again our small box of fluid, a fluid element, this is changed in time, if we have flows of energy in or out of the system. And so this behaves in exactly the same way as the mass or momentum did, that we have flows through the surface. So we have flows through the surface of E, and then we have a advection velocity U dot ds. So this is the flow through the surface of the energy. And if it's positive, energy is flowing out, and then the energy inside is reduced. And like the other equations, here we have a sources as well. So we can not only move energy from one point to the other, we can put energy into the system, for example, by compressing the gas. So if we take a box of gas and we compress it, we do work on the gas, and the internal energy will go up. Or alternatively, if you push the box on one side, the fluid will accelerate, and we'll be putting kinetic energy into the system. In either case, we're doing work, we're putting energy into the system, and we're changing E. So we have a source. So we have here like an external source of energy. Source of energy. So this is some external source of energy which we're putting into the system. And so we can write this essentially as this is the work done on the system, which is this here is the work done, essentially plus the heat, So if going back to thermodynamics, the first law of thermodynamics, you have the change in energy. Energy of the system is the work done and the heat that's put into it. So in this case, what we're going to do for now is we're going to neglect the heat. So we're going to assume that part is 0. And that's a big assumption. We'll come back and discuss that very shortly. For now, we'll just consider the work done on the system. So again, if we have a sort of box of fluid, and we consider what happens. So here again, I have a little box of fluid. We have forces on the sides of the fluid. So we have a pressure. We discussed for a moment. We have a pressure just pushing on the outside of the fluid. If the fluid moves under this pressure, then we have a force and we have a distance. So we have work being done. And so the work done per area on each little area of the surface is just pressure times the flow velocity. So it's how fast the fluid is moving, dotted with the area. So if the size of the box moves, this gives us essentially force times distance per second. So this is an energy per second times area. So this has units of area. This is basically meters squared. This has units of meters per second. And this has units of basically joules per volume. So it's joules per meters cubed. And you can see the whole thing just gives us joules. So this whole thing just gives us joules per second. It's the units that come out of here. And so this is the change in energy of a system, is the work being done on it. And so the total source of energy is we add up all the work being done over the entire surface. And so this work done here is just the integral of this over the whole surface of the box. So every side of the box could be moving under a pressure, and so every side could be doing work or having work done on it. And so this work done here is equal to, so total work done, so total work done is just the integral over the surface of this quantity here. So it's P times U dot ds, so the perpendicular motion of the fluid to the surface. So we have Pu dot ds. It gives us the total work done by the fluid. So remember, if U dot ds is positive, then the fluid is moving outwards, and if it's moving outwards, it's doing work against the external pressure, so it's losing internal energy, and so we have basically a minus sign in this bit here, so put in here. So we have a d by dt of the integral of the energy inside the volume. Again, is the flow of energy due to fluid flow ds, and the work being done. So we have, we have a minus sign here, just copied from this above here, and we have this extra work being done here. So we have a minus the integral again over the surface of pu dot ds. And so this is basically the integral form of the energy equation. And as before, we can convert these surface integrals into volume integrals of the divergences, and so we can just write down this is dE by dt, and here we have a divergence. So this component here of the flux, so this is EU, and here we have the work done, and here we have a divergence of P times U. And there may be other terms here, so we've had sources or sinks. So the one major one we missed out here was the heat. So if you have flow of heat in or out of the system, that would give us extra terms in this equation. And so one here, I'll just note here, plus heat. So in the Euler equations this is missed out, but in general this will give us another quantity we have to calculate. So here we had sort of heat flux or heat flow through a surface. We call it Q, for example, and we'll come back to this later, but we'll see it in a more rigorous derivation of these equations. We have this heat equation, and this in principle would give us another equation. So we'd have, in order to calculate the heat flux, we need another equation, and that other equation would have another term which again we couldn't calculate, and so this goes on essentially forever. And so what we've done here is we've stopped this infinite series of equations. We've truncated it by just saying that this extra term is 0. But in general, there are other treatments that can be done for this, and we'll see a few of these in the next few lectures. But this in general is called the closure problem. This is the closure problem. So each equation depends on another equation. So each equation depends on the next. So the equation for the mass density depends on the momentum depends on the energy depends on the heat flux, and the heat flux depends on things that don't have a name, but it keeps going on and on. Okay, but now we have, because we truncated it here, we've just said that there's no heat, so this heat is 0, so it's an adiabatic assumption. So here we have made that the heat flow is 0, so this is an adiabatic. So it's an adiabatic assumption, and this has led us to a closed set of equations which don't depend on anything else we don't know, which are called the Euler equations. So we have equations for the mass density. So I'll just try to summarize them here. So these are the Euler equations. So we have an equation for the mass density, d rho by dt. Let's write them in this form here. So we have divergence of rho u. So this is the first equation we derived. So this is the mass density. We then have an equation for the momentum as well. So we have a d by dt of rho u. And now here we have a divergence of momentum flux, rho u, and this is equal to minus grad p. And then we have the equation we've just derived now, which is for the energy, and so here we can write this down as d by dt of the energy, so turn this into E, of the energy. And here we have a divergence of, I'll write this down here as E plus P U equals 0. So I've just grouped together this term here. So you can see this term here and this term here with the E and the P. We've just grouped together. There's E plus P here. And so here we have mass, we have momentum, and we have energy. And that's it. These are the three fluid equations. You may be saying this is not the form I remember, or I've seen different forms. There are many different ways of writing the Euler equations. And so next talk I'd like to do is go through the different ways of writing this equation. And some of them are useful for some things and some are useful for other purposes. And in doing that we'll see some other concepts like the advection derivative, and that will be useful as well for understanding what these equations mean and how to manipulate them. Okay, see you next time.